The black hole. Many say it represents the limits of human understanding. True to its name, the black hole is always dark, bizarre, and terrifyingly mysterious. Today, black holes are one of the key subjects observed by humans in outer space. But did you know that it wasn't until 2019 that we finally obtained the very first image of a black hole? Before that historic photo was released, black holes only existed in theories or in humanity's most complex physics equations. But after that moment, everything became clear. Black holes are real, and everything people had said about them up to that point turned out to be true. To us, black holes are both mysterious and terrifying objects. Yet they hold humanity's deep desire to understand the universe. So, what do we actually know about them? How terrifying are they really? And could a human survive if faced with a black hole? Today, we'll explore the most powerful monster in the universe, the black hole, and how humanity might survive an encounter with it. As always, don't forget to leave a like and subscribe to support the creators behind this video. We hope you'll enjoy today's content. A black hole is a region of space-time where gravity is so strong that nothing, not even particles or electromagnetic radiation like light, can escape its pull. According to the theory of general relativity, when a massive amount of matter is compressed into a small enough space, it distorts the fabric of space and forms a black hole. Surrounding the black hole is a boundary known as the event horizon. Once any matter crosses this point, it is pulled inward and can never return. The black hole is called black because it absorbs all matter and radiation that pass through the event horizon, similar to a perfect black body in thermodynamics. According to their formation and properties, black holes can be classified into three types: stellar mass black holes, intermediate mass black holes, and supermassive black holes. Stellar mass black holes are those with masses about 10 times the mass of the Sun, formed by the collapse of massive stars. This type of black hole is the most common, and many such black holes have been discovered to date. Intermediate mass black holes fall between stellar mass and supermassive black holes, with masses ranging from a few thousand to 1 million times the mass of the Sun. However, there are still debates among scientists about how these types of black holes are formed. Supermassive black holes are the heaviest black holes in the universe, with masses ranging from millions to billions of times the Sun's mass. Scientists believe they may form through some special mechanism, such as the merger of galaxies. In other words, they could also be created when two or more black holes merge into one. Although by definition, a black hole is a completely dark or invisible region, its existence can be inferred through its interaction with surrounding matter and light radiation. Matter falling into a black hole forms an accretion disk. Here, the matter collides and rubs together, becoming plasma that emits intense radiation, making the area surrounding the black hole one of the brightest objects in the universe. If a star orbits a black hole, the shape and period of its orbit allow astronomers to calculate the black hole's mass and its distance. This data helps them distinguish whether a superdense object is a black hole or a neutron star. In this way, many black holes have been discovered in binary star systems, and at the center of the Milky Way lies a massive black hole with a mass of approximately 4.3 million times that of the Sun. One common misconception people have about black holes is thinking of them as extremely dense objects. As we mentioned earlier, while black holes do form from extremely dense matter, the black hole itself is, in fact, nothing at all. Our Sun has a diameter of about 1.5 million kilometers. But if we were to compress the sun into a much smaller size, smaller and smaller, until it became a sphere just 6 kilometers in diameter, its immense mass would force it to keep collapsing and then disappear. No surface, no physical matter creating it. All that would remain is an empty region of space. If you approached a black hole, you might not even realize something terrifying was near. Suppose you were on a journey through space to enter and explore a black hole. How do you think that journey would go? Could you survive and escape from it? To explain this, we need to take a moment to understand what curved space-time inside a black hole really means. Since the 20th century, Einstein's equations have described how space and time respond to matter and energy. You can search the keyword Einstein field equations to learn more about those equations. If you throw something around the Earth, you'll see it move in an arc. If you throw it fast enough, you can put it into Earth's orbit, and it will travel along a perfect curved path. We have examples of this, like the International Space Station, ISS, for instance. It was launched at over 28,000 kilometers per hour on a curved path that is actually a continuous fall, or more precisely, a perfect orbital curve around Earth. Its engines are off, and it is literally falling around our planet. The orbit of satellites, or the ISS, illustrates how curved paths appear in space. So if you're exploring space and don't realize you're approaching a black hole, you could get very close without warning. That's because no light escapes from around a black hole. A black hole acts like a lens, distorting the light around it due to the curvature of space. But instead of focusing or spreading the light like a normal lens, it bends the light infinitely. We'll explain this more clearly when we discuss the black hole photograph in the next section. Back to the journey. If you realize you're near a black hole, by then it's already too late. You'll almost certainly be trapped by it, and any effort to escape will be useless. Even if you somehow had a way to steer your spacecraft away, the first problem you'd face would be the fuel you have on board. Let me help you understand why, by explaining the challenge of escaping Earth's gravity. Do you know how fast a spacecraft must travel to enter Earth's orbit? Only at a speed of 7.9 kilometers per second can a satellite or spaceship avoid falling back to the surface. Spacecraft on the moon require a speed of 11.2 kilometers per second, and even higher speeds are needed to reach other planets. So how do we reach such speeds? Only rocket boosters are powerful enough to handle it. To accelerate an object to 7.9 kilometers per second and escape Earth's gravity requires an enormous amount of energy. If you found this video interesting, don't forget to hit like and subscribe so you won't miss the next exciting adventures. To escape Earth's gravity, an object weighing just 1 gram would require an amount of energy equivalent to powering 1,540-watt light bulbs for 1 hour. On the other hand, rockets work by expelling gas from the rear to generate thrust. The faster the gas is expelled, the faster the rocket travels. To reach extremely high speeds, not only must the gas be expelled at very high velocity, but the rocket must also carry a massive amount of fuel. Assuming an exhaust velocity of 4,000 meters per second, in order to reach escape velocity of 11.2 kilometers per second, the rocket would need to carry fuel several times its own weight. Now imagine the kind of gravitational pull a black hole generates, with a mass millions of times greater than the sun. Even if the spacecraft could withstand that pull, where would you find enough fuel to help it reach the escape velocity required? Once you've entered the black hole's range of influence, you simply cannot escape. At this point, the answer to whether you can survive and get out of a black hole is clear. There is absolutely no way. As you approach a black hole, not only is space bent, but time is distorted in the same way. The intervals between each tick of a clock, between each breath, between each stream of thought, seem to slow down compared to someone far away from the black hole. For you, however, the experience of time feels completely normal because you've become synchronized with the time reference frame near the black hole. And as you get closer to the region of infinitely curved space-time at the center, an outside observer would see your clock appear to freeze entirely. But that's not all. After a while, if you're still alive, you will cross the place known as the event horizon. This is the region where no matter can escape, including light. Once you pass this point, as you're being pulled toward the event horizon, you will experience a unique effect called spaghettification. Roughly translated as the noodle effect, this is one of the most famous phenomena caused by a black hole. It's easy to imagine anything that gets too close to a black hole will be stretched out like strands of spaghetti. This effect is caused by the uneven distribution of gravitational forces on the object. Imagine you're being pulled toward a black hole with your feet leading. The gravitational pull on your feet will be stronger than on your head. It doesn't crush you, but stretches you out. Even worse, your limbs are no longer aligned with your body's center of mass and are pulled in different directions. As a result, your body stretches out as if it were made of elastic. You might imagine it like the character Richard from Fantastic Four, but on a much more terrifying scale. It stretches and tears apart both you and your spaceship down to the molecular level, disintegrating you into nothingness, to the point where you are no longer any known form of matter. At that moment, you are nothing. But let's continue the hypothesis. Somehow, by a miracle, you and your ship pass through this region. So what awaits in the next areas? Any object that goes deeper into a black hole must face even more extreme conditions. The center of a black hole, known as the singularity, is a place of infinite density and gravity within an extremely small volume. It is a region where classical physics no longer applies, and only the combination of quantum mechanics and general relativity may offer partial explanations. When matter falls into a black hole, it may completely vanish or become part of the black hole itself. We still don't know its true fate, which only adds to the mystery surrounding black holes. This has led to many fascinating theories. If you've seen Interstellar, 2014, you may remember the scene where the main character is pulled into a black hole, crosses the event horizon, and enters a five-dimensional space shaped by gravity. In this strange dimension, no light or sound can escape, as if it were a world entirely cut off from the universe we know. The idea of a five-dimensional space was proposed by the scientific advisor for the film Interstellar, Kip Thorne, a renowned theoretical physicist from the California Institute of Technology. This hypothesis is fascinating because it describes a black hole as a kind of photocopier of the universe. It suggests that the black hole has another surface, and things don't get sucked infinitely deep inside, but instead fall onto some kind of surface. Think of counterfeit postage stamps, which contain a virtual surface. The surface of a black hole is thought to be similar. If this is true, you might remain intact on a surface inside another spatial dimension. However, this surface has all the necessary information to describe a three-dimensional object, so you would be tricked into not realizing that it's just a projection. This means that, who knows, we might already be living inside a black hole right now. But things could go far beyond what you can imagine. Not just the Earth, the entire universe might already be inside a black hole. And this could mean that black holes might help us unlock the origin of the universe itself. Many people have always wondered, If the Big Bang started everything, then what existed before the Big Bang? We know that the Big Bang happened about 13.7 billion years ago. Just 10 to the power of minus 36 seconds after the explosion, space expanded like a balloon. Before the Big Bang, some researchers believed the universe existed as a single, dense, and infinite point, called a singularity. That singularity exploded and has been expanding ever since. This is essentially the opposite of the nature of a black hole. A black hole is also a dense and infinite point in space-time. However, instead of expanding and releasing everything, it pulls everything inward. But if our universe is inside a black hole, as it keeps pulling in matter from the outside, it makes sense that the inside would keep expanding. Could it be that the formation of a black hole means the creation of a new universe within it? At present, some believe it's entirely possible that black holes could reach such massive sizes that they might contain an entire universe inside. However, the largest black hole ever discovered is TON 618. It's unimaginably massive, with an event horizon over 390 billion kilometers wide, 43 times the diameter of our solar system. This size is still too small to contain even a galaxy, let alone the entire universe. So how could the whole universe possibly fit inside a black hole? Our universe is expanding so fast that we may never reach its edge. Due to the open curvature of space-time, it's very likely that our universe has a shape similar to a donut. If you try to reach the edge of the universe, you'd just go around in a loop and end up back where you started. Just like you can't reach the edge of the universe, you can't reach the center of a black hole either. So, if our universe exists inside a black hole that belongs to another universe, then reality may consist of overlapping universes, each containing black holes that hold their own separate universes. If you found this video interesting, don't forget to hit like and subscribe so you won't miss the next exciting adventures. The black hole universe theory could help us solve several other problems in physics. Specifically, it may offer an explanation for dark energy, the mysterious force driving the universe's expansion. No one truly knows what dark energy is or why the universe not only continues to expand, but does so at an accelerating rate. So what if that dark energy comes from matter outside our black hole universe being pulled inward? That external matter might become internal energy, fueling our universe's expansion. This idea could also explain the early and sudden inflation of the universe right after the Big Bang. However, while the black hole universe theory might answer some big questions, it also raises others. We still don't know exactly how external matter transforms into internal energy. That remains an unsolved mystery. But even if one day we manage to solve all of those issues, there's still one major question left. How can we test whether we are truly living inside a black hole? The answer to that might have to wait for much greater breakthroughs from future scientists. Here's another fascinating theory about black holes. We could actually use them for time travel. As mentioned at the beginning of the video, when space is stretched, time is as well. A clock near a massive object runs slower than one near a smaller object. So, a clock near a black hole would tick slower than a clock on Earth. 1 year near a black hole could equal 80 years on Earth, as illustrated in the movie Interstellar. In this way, a black hole could let us see the future. If you wanted to visit Earth's future, all you'd need to do is fly close to a black hole, then return to Earth. If you get close enough, your clock slows down. But as long as you don't cross the event horizon, you can still escape. Of course, this is all theoretical. As we've discussed, no spacecraft today has the power or fuel to escape a black hole's influence. But what about the past? That's where things get really interesting. A black hole may bend time to the point of infinity. Imagine you take a sheet of paper and connect its two ends to form a loop. That's what a black hole can do with time. It creates a natural time machine. If somehow you could enter that loop, you'd find yourself moving along a path through space, starting in the future and ending in the past. Inside the loop, cause and effect become difficult to distinguish. Events from the past create the future, and the future in turn causes events in the past. Let's say you discover a black hole and want to use a reliable spacecraft to go back and visit the dinosaurs. There are two important limitations. First, you can only travel into the past that belongs to the black hole itself. This means if the black hole formed after the extinction of the dinosaurs, you can't go further back than that point. Second, you might need to cross the event horizon to enter the time loop. And to escape the loop at a specific moment in the past, you would have to move faster than light, something that, as of now, is impossible. So, while it's fascinating to think about the time-bending properties of black holes, visiting dinosaurs or traveling to the future will remain impossible in the near future. Although black holes are among the most mysterious objects in the universe, our understanding of them is still very limited. Scientists are working hard to study the nature and behavior of black holes, hoping to uncover the secrets they keep hidden. By observing the radiation around black holes and using advanced simulation techniques, we may gain deeper insight into the harsh environments and astonishing phenomena that matter encounters when falling into them. However, the day we truly explore a black hole directly is certainly not coming anytime soon. You might not believe it, but despite studying black holes for hundreds of years, we only captured the first real image of one, just a few years ago. Indeed, the history of black hole research is like a centuries-long television series, and the very first photo of a black hole was the result of countless brilliant minds working over hundreds of years. The idea of a massive object so dense that even light couldn't escape from it was first proposed by a man in a letter to the famous English physicist Henry Cavendish in 1783. John Michel described that if the radius of a spherical body with the same mass as the Sun were more than 500 times smaller than the Sun's radius, then an object falling from infinity toward it would reach a velocity greater than the speed of light upon hitting its surface. And if light were also subject to gravitational attraction, just like ordinary matter, then any light emitted from the surface of such a sphere would be pulled back by its gravitational force. In 1796, French mathematician and astronomer Pierre-Simon Laplace also proposed this idea in the first and second editions of his book, Exposition of the System of the World. If you found this video interesting, don't forget to hit like and subscribe so you won't miss the next exciting adventures. In the 19th century, the idea of dark spheres, objects so massive that light couldn't escape, was largely forgotten. Most physicists at the time believed light had no mass and thus couldn't be affected by gravity. This concept seemed destined for obscurity until Albert Einstein came along and changed everything. In 1915, he introduced the general theory of relativity, predicting that gravity could bend the path of light. Just 2 months later, astronomer Carl Schwarzschild discovered the first exact solution to Einstein's field equations. His solution described the gravitational field of a point mass or a uniformly distributed sphere in curved space. This led to the birth of the Schwarzschild radius, a boundary in space-time. If an object is compressed within this radius, it becomes a black hole. This discovery not only provided the mathematical foundation for black hole physics, but also marked the beginning of the golden era of general relativity. Today, black hole physics has become one of the most important fields in modern theoretical physics, pushing the boundaries of our understanding and fueling humanity's quest to unlock the deepest mysteries of the cosmos. We had another major discovery with pulsar, rapidly spinning neutron stars, in 1967. However, until that point, physicists still considered neutron stars to be similar to black holes. Following that, groundbreaking research by Stephen Hawking and many other distinguished scientists in the early 1970s gave birth to the field of black hole thermodynamics. These laws describe the properties of black holes using concepts similar to the laws of thermodynamics, relating mass to energy, event horizon area to entropy, and surface gravity to temperature. In 1974, Hawking completed these theoretical connections by proving that quantum field theory in curved spacetime predicts that black holes emit radiation proportional to their surface gravity. The term black hole was first introduced by physicist John Wheeler during a lecture in 1967. Once Wheeler popularized the term, it quickly gained widespread usage among scientists and the general public. The journey from the first concept to the naming of the black hole was already long and full of challenges. But the journey to capture the very first image of a black hole was even more difficult. Take a look. The image we're seeing is the result of collaboration among 8 observatories across the globe and over 200 leading astronomers. Scientists from the EHT project, the Event Horizon Telescope, used 8 telescopes positioned around the world to create a virtual telescope the size of Earth, capable of capturing the black hole's image. The image released is of the black hole located at the heart of the galaxy Messier 87 in the Virgo supercluster, nearly 55 million light-years from Earth. This is the first actual image of a black hole in the universe. All previous visuals we had were either artistic illustrations or computer-generated simulations based on scientific data. However, unlike the dramatic renderings of glowing rings around a dark sphere, the first real image of M87 revealed only a mysterious circle in hues of yellow and orange. Why is that? Could it be that we've misunderstood black holes all along? Why doesn't it look as majestic as we imagined? The answer lies in the fact that movies rarely reflect reality. Even this photo, though indeed a real image of a black hole, is not a direct image. What we're seeing is actually the shadow of the M87 black hole. Theoretically, a black hole is an invisible object. However, we can still observe the outermost edge, known as the event horizon, under certain conditions. For example, if the black hole is surrounded by a glowing disk of gas. In such cases, the black hole casts a clear dark region in the center, like a shadow projected against a bright background. The black hole at M87 isn't the closest to Earth, but it's the most massive one ever observed. That's why it was considered the most promising target for the EHT project. In the image released by scientists, the black circle in the middle is simply the shadow of the black hole, while the bright ring surrounding it is made up of luminous matter spiraling toward the event horizon. However, the colors of the ring in the image aren't the actual colors of the gas and dust around the black hole. The orange-yellow tones we see were chosen by EHT scientists to represent intensity of brightness. Yellow indicates the brightest areas, red represents lower intensity, and black shows regions with little to no light. If we analyze the light spectrum from the ring around the M87 black hole, it would likely appear white with hints of blue or red. Over time, human understanding of black holes continues to grow. We have every reason to dream of a future where this cosmic monster is fully decoded. At that point, theories about time, matter, the event horizon, or even a fifth dimension may finally become clear. What do you think about the study of black holes? Is it a subject worthy of our effort and curiosity? And if we truly unlock the secrets of black holes, could it open a new chapter in the history of science? Thank you for listening and supporting today's video. See you next time, and have a great day with your loved ones. If you found this video interesting, don't forget to hit like and subscribe so you won't miss the next exciting adventures.